Hi, my name is Ben Addix, and today I will show you how to create a personalized recommendation using machine learning on Amazon SageMaker. Amazon SageMaker helps data scientists and developers to quickly prepare, build, train, and deploy machine learning models by bringing together a broad set of purpose-built capabilities. For this demo, we'll be working in SageMaker Studio, which is a fully integrated development environment for machine learning. Personalization, at the highest level, describes how an organization delivers more customized interactions and unique experiences for users. It is a means to meet user expectations by delivering the right experience at the right time and the right place. The concept of personalization, although not new, now offers organizations the ability to improve brand loyalty, grow revenue, and increase efficiency by using data to create a more sophisticated and customized customer experience. With traditional approaches to personalization, they're typically based on broad segments of users, not tailored for every individual user, and therefore the recommendations oftentimes miss the mark. Machine learning provides a scalable way to deliver unique experiences to individuals based on their behavior and inferred preferences, rather than generic segments of users. Machine learning can help by processing customer data and selecting the right algorithms to dynamically present the most relevant products or content to each user at the right time. For today's demo, I will show how to use SageMaker Studio, Lineage, Model Registry, and pipelines to build, train, and deploy a personalized recommendation engine using e-commerce data. This will be a great opportunity for data scientists and developers new to AWS and SageMaker Studio to explore some of the SageMaker features in action and be able to quickly create their own personal solutions to fit their business needs. To get started, we'll need to launch SageMaker Studio. From within the SageMaker console, we can select Amazon SageMaker Studio in the top left, and we'll be taken to the SageMaker Studio control panel. Here we can see all SageMaker Studio users associated with our account. If there are no users, you can create one by clicking the Add User icon in the top right. I already have a user here, so I will click Open Studio, and this will take us to our integrated development environment. And just like that, we're in a Jupyter environment and can begin our data science development work. Once we're in SageMaker Studio, we're presented with this launcher. The launcher has a variety of different features that we can take advantage of. For example, we could start a new data flow, or we could start by creating our own Jupyter notebook. We also have the Files icon in the top left, where you can see any folders or notebooks that are available. Here it's empty because there are no folders or files available yet. But for this demo, we will need to clone the AWS Personalization repository. So to do so, we can click the Git icon and then click Clone a repository. And then we type in the name of the repository that we're using. We then pass in our credentials. And then once we click clone, it'll take a few seconds, and then our repository will now show up in this files icon. Once the repository is cloned, we can click in and open our notebook. The example notebook that we're going to go through today is using a SageMaker built-in algorithm called factorization machines in order to predict which products to recommend to different users. A factorization machine is a general-purpose supervised learning algorithm that you can use for both classification and regression tasks. It is an extension of a linear model that is designed to capture interactions between features within high-dimensional, sparse datasets efficiently. For recommendation engines, we typically only have high-dimensional sparse data since most customers only buy a tiny subset of all of the products offered. Factorization machines are particularly well suited for this kind of data set. For the overall flow of this notebook, first we will read in the data, then do some data cleaning and feature engineering to prepare the data for model training. Second, we'll train our model using SageMaker's built-in factorization machines algorithm. Third, we'll use Amazon SageMaker lineage tracking to track several artifacts from our model. Fourth, we'll create a model package group to register our model in the SageMaker model registry. And finally, we'll use SageMaker pipelines to create a pipeline which will contain all of the aforementioned steps and allow us to automate them. Before we begin, let's make sure we have up-to-date versions of SageMaker and Boto 3. Next, we'll run a store magic command, which will let us save checkpoints throughout the notebook. This way, if we ever terminate the kernel, but then later need to pick back up in the notebook, some of our variables will be stored for us already. For example, we will not need to fit our estimator again. Next, let's import the packages that we'll need, including Boto 3, SageMaker, and different SageMaker lineage and workflow methods. Next, we'll configure our SageMaker client and session. Now that we have our configurations done, we're ready to begin looking at the data. We start by importing our data and taking a look at the first few rows. The data is online retail data from the UCI machine learning repository, which spans 1 year's time. We can see that we have transactional data containing invoice numbers, stock codes or item IDs, product descriptions, quantity sold, date of purchase, price, customer IDs, and country of customer. Since we don't have customer ratings in our data, we will use the quantity purchased as a proxy for rating. In other words, we will try to predict quantities, and if we predict a higher quantity for a certain customer product combination, we will take that to mean a higher likelihood that the customer will purchase a given product. If we did have a customer rating, we could use that for our prediction instead. For example, if we had thumbs up or thumbs down ratings, then we could use factorization machines for binary classification. Now, let's do some pre-processing and visualizations of our data. We'll need to do pre-processing to format the data so that it's suitable for machine learning. Machine learning models can only take numeric inputs and cannot handle missing data, so we will need to remove any missing values and convert our categorical and text-based columns to numeric representations. First, we check to see if there are any null values. There are a substantial amount of missing customer IDs. If we don't know the customer, then it will not be helpful for us when we're making recommendations. Therefore, let's drop these records. Turns out that the rows with the missing descriptions also happen to be rows with missing customer IDs. So when we drop the rows with missing customer IDs, the rows with missing descriptions go away as well. Next, let's plot the unit price distribution. We can see that we have no negative values, which is good, but it does seem like there are some extreme outliers. For now, we're not going to have to do anything to handle that because items with high prices are relatively normal. Next, we can look at a distribution of the quantity. Here we see a largest spike around 0, meaning small quantities, but we do also see very large negative and large positive quantities as well. These negative quantities might not make intuitive sense, but it turns out that that's how cancellations or returns are handled. In this case, it looks like someone placed a very large order of 80,000 units, and then that was subsequently canceled by the negative 80,000 negative quantity. This happens throughout the dataset, and since quantity is our target, we need to make sure that it's relatively clean and without these large positive and negative amounts that cancel with each other. To do that, let's aggregate the data over the year and take the sum of the quantity. Therefore, any transactions that are associated with a cancellation or a refund will go away. We will also make sure that all final quantities are greater than 0. Now we still have some categorical features, and we will need to handle them before training a model. Handling these categorical columns will create many additional columns, resulting in sparse data. Sparse matrices are our friend here because they allow us to store all the data without running into memory errors. Since the description column is text-based, we can apply text featurization to it. The method that we will use is TF-IDF, which stands for Term Frequency Inverse Document Frequency. TF-IDF considers each term in the descriptions and measures how relevant that term is to the description compared to how relevant it is for all descriptions. For example, we can see that there is a description for white metal lantern. The output of our text featurization will give us a column for each of those 3 words, and the values we weighted based off how frequent those words are in other products. For the stock code, customer ID, and country, the values are distinct categories. Therefore, we will one-hot encode those. As I mentioned before, this will leave us with very sparse data, since most users only buy a small subset of all products. For other algorithms, we might want to choose a different approach for building the dataset, but for factorization machines, it handles sparse data very well, and is designed for users and products to be one-hot encoded this way. In the end, we are left with a sparse matrix where the rows are each product that a user bought, and our columns are all of our features. The stock codes, the customer IDs, country, unit price, as well as our target, which contains the quantity. You can see that our data is over 99.9% sparse. But like we mentioned, factorization machines are designed to handle this kind of sparse data, and it will not cause any issues. Next, we split our data into training and testing sets. Then we write the data to protobuf record IO format, because factorization machines take the protobuf record IO format as an input. Using this format allows you to take advantage of pipe mode. In pipe mode, your training data streams data directly from S3. Streaming data can provide faster start times for training jobs and better throughput. Now, our final data is stored in S3 and we are ready to move on to training. Here, we define our factorization machine estimator, including parameters such as the instance type, the instance count, as well as the hyperparameters to train the model. We can then fit the model, passing it our training and testing data. Calling .fit kicks off the training job. This will take a few minutes to run, and we will pick back up once it's complete. Once our model is trained, we will want to use SageMaker ML lineage tracking to track different artifacts about the model. An important aspect of transparency in machine learning is to be able to link a model with the code and data used to train it, so we can easily find how any given model was produced. In the event that a model begins to start performing poorly, we should be able to quickly find all of the artifacts used to create it so we can debug the problem at the source. To do this, we need to create an artifact for every aspect of training we'd like to save. First, we will create an artifact containing training data. Then we will create an artifact containing the model itself. We can then set the associations for these artifacts. Now for the SageMaker model registry. Here we start to create a model package group in order to store the model metadata, including the artifacts such as the data and model parameters. This allows you to gain visibility and reproducibility of the process by which we create the models. We create model package groups that contain different versions of a model. You can then register each model you train, and the model registry adds it to the model group as a new model version. So if you plan on tracking multiple versions of a model, you need to create a model package group first. Once the model package group has been created, you can now add the first version of your trained model to it. We will only show one version of a model here, but in practice, you may have different versions as you try different features, different hyperparameters, or even update your model over time. Along with the S3 location of the trained model, you need to add the inference specification so we know what Docker image to use to deploy the model and make the predictions. We can also use various training metrics like training and validation, root mean squared error. Here we include every metric that is associated with our training job. Finally, for model governance reasons, we can tag the model package with a status, so it's easy to tell which models are actually approved or declined for deployment into production. Here, we tag this one with pending manual approval. Now that we've built our model, we probably want to get predictions back from it. Let's look at a single customer and try to find which products to recommend. First, we define a serializer, which is used to encode data for an inference endpoint, and a deserializer, which decodes data from an inference endpoint. Next, we will make inference for this customer and any items in our catalog, and then we can recommend whichever products return the highest values. Next, we'll find the top customer, who's the customer who spent the most money over the entirety of the data set. We will then try to make inference for this customer and any items in our catalog, and then we'll recommend whichever products return the highest values. Here I'll search through the top 100 most popular items to figure out which to recommend, but alternatively, you could search through all products in the catalog. We then need to perform the same transformations to the sparse vector as we did before. We then will call .predict to get our predictions back from the model. Then by parsing and sorting the results, we can figure out the top products to recommend. Here I will look at the top 5 products for this customer. And we can see that the top recommended product is Regency Cake Stand 3-tier. In our final step, we will take each of the steps shown before and work them into an automated workflow using Amazon SageMaker pipelines. Model training is not a one-and-done task. You will want to improve your model with new data, as well as changes in customer purchase behavior over time. Improving models takes thousands of repetitions of all the steps we just went through. Having these steps automated using pipelines allow us to replay the whole workflow with a single click and save hours of manual work. First, let's upload our raw data to S3. We will then set a model approval status of approved, meaning this model is approved for production. In practice, you might want to set this to pending manual approval so that someone needs to go in and manually approve the model for production later. Next, we define a custom step for preprocessing our data. Our preprocessing.py file has all the transformations that we performed above, including splitting the data into training and testing sets and saving them to protobuf formats. We specify the outputs to contain both the training data and the testing data so that we can use them in subsequent steps. SageMaker comes with a pre-made training step in the SageMaker SDK, which abstracts away most of the generic processor code. All we need to give this step is the estimator and an input, which in this case is the training and testing data. These are the same training and testing data that we defined above. By defining the inputs to this step as the outputs of the previous step, it informs SageMaker that this step has a dependency on the previous step and cannot be executed until the previous step has finished. Similarly, the SageMaker SDK has another convenient step called the Create Model step. The Create Model step takes an image URI and the model data input from the previous training step. This step creates a model for use in transform steps or later publication as an endpoint. Next, we define a register model step. The register model step creates a model package resource in the model registry that can be used to create deployable models in Amazon SageMaker. Our final step is for deploying the model. There is no pre-made step for model deployment, so instead we'll create a processing step where the deployment happens inside that processing step. Once all the steps have been defined, we add them to the pipeline class in the SDK, along with the processing input variables that we created at the outset of our pipeline. Upserting the pipeline registers the pipeline with SageMaker, and then calling the start method will kick it off. Once the pipeline is kicked off, we can view the pipeline in the sidebar and track its status there. In the sidebar, we click SageMaker Components and Registries. We can then go to our pipelines and view the status of the pipeline that we just created, as well as clicking into it, which will give us the directed flow of all of the steps that we just created. Well, there you have it. In this demo, we showed you how to integrate various SageMaker features, including a SageMaker built-in algorithm, the factorization machines, model training, model lineage, model registry, deployment, and pipelines. We built a recommendation engine for e-commerce data, which can make it easier to create personalized recommendations for your customers and enhance the customer experience. Happy building!